All right, we'll get started with the next session. So thank you everyone again for joining the fourth annual International Day of Women in Statistics and Data Science. This next session, session 205, is going to be a speed session. So each presenter will have 5 minutes to speak. So we're going to start off with our first speaker, Emily Gentles. Thank you so much. And just let me know when you want me to go to the next slide.
Sounds good. Yeah, we can go. Perfect. So my name is Emily Gentles, and today we're going to be talking about record linkage and recent developments in efficiency and privacy, although we're going to be focusing more on that efficiency piece. This is a pretty quick session, so I went ahead and just put my QR code to my LinkedIn on the bottom left corner there. So it'll be on all the slides, so feel free to connect with me if you end up having a question or want to know some of the papers that I'm referencing. If we could go to the next slide. So what is record linkage? Record linkage is when we have two or more data sets and we're interested in determining if two records refer to the same entity. So here we see database A and database B, and we have name, date of birth, and address information for each record. For this particular example, we see that the name is similar, the date of birth might be exact if the month and day were reversed, and the address is also pretty similar. So based on this information, we can calculate the probability that this refers to the same person. However, you can imagine that if we want to compare every record to every other record, the amount of comparisons increases very quickly. I'll quickly note also that privacy preserving record linkage is a kind of extension of record linkage where we would be doing this linkage without any of this personal identifying information. So we can advance to the next slide. With so many different comparisons, we need to be able to do this efficiently. So we're going to go over some ways that you can improve the computational component of record linkage. I think one of the ones that is the most heard of is blocking. This is where we reduce the search space. So we might search within only one date of birth year. So we might only try to match people who were born in 1990 because it's unlikely they would be matching with someone who's born in 1980. We can also use unsupervised learning to help calculate our parameters on the fly instead of using training data to first calculate those parameters and then rerun our entire model. You can also use improvements of existing algorithms, like using the approximate EM algorithm instead of just the EM algorithm. We can also take advantage of all of the data management optimizations that exist in our modern programming languages, like using sparse matrices, sparse matrix calculations, as well as parallel processing. We can also optimize our algorithms for sparse comparisons. Most of the comparisons that we're making are not going to end up being matches. So if we can only compare likely matches and not compare matches that are very unlikely, that we can really drastically reduce the amount of comparisons that we need to do and reduce the amount of computation. We go to the next slide. So there's also specific computational improvements for Bayesian methods specifically. I think perhaps it's well known that Bayesian methods tend to be very computationally complex and slow already. So when we're trying to use large data sets, they can really get bogged down. So this is where some exciting improvements have been happening. There's some papers that came out this year that had some pretty drastic improvements in speed. Some of the things that they were able to develop is storage efficient indexing. Essentially, we're doing a lot of bookkeeping when we're keeping track of which matches might be matches, the second best match to compare to. If you have big data sets, that's a lot, it's a big array to keep track of all of those indices. So if we can figure out how to store those more efficiently, which this paper was able to do, then we can save some time and some resources there. Bayesian methods are also typically using Gibbs samplers, so if we can reduce the complexity of those, that can drastically improve our speed. We can also use independent priors. So there's a single prior typically put on the latent indicator variable that represents the true matching status of a record pair. So this is how much we believe that the match that we're looking at is a true match prior to running the model. So in Filagi Center, which is the foundation methodology for probabilistic matching, they use one prior. However, this paper found that they used independent priors. They were also able to greatly reduce the complexity of their model and speed up that process. So there's a lot of R packages in this space. Some of them that use the techniques that I listed here are FastLink, which is a great package to look into. And yeah, feel free to reach out if you want to know more. But thank you so much.
Great, thank you so much, Emily. Our next speaker is going to be Cheyenne Amoroso. So just let me know when you want me to continue to the next slide.
Good afternoon, everyone, and thanks for joining. As the chair said, my name is Cheyenne, and I am a PhD student at the University of Coruña in Spain. And today I'm going to talk about a collaborative project between the University of Coruña and the Spanish Statistical Office, where our main goal is to obtain long-time series that are properly seasonally adjusted. So let me start by introducing what is seasonal adjustment. As many of you know, time series can exhibit a variety of underlying patterns that contribute to the observed changes over a period of time. These patterns are crucial to understand the dynamics within the data and can be broken down into three main components. The trend component that represents the long-term movements in the data, the seasonal component that captures periodic fluctuations that occur within known time steps, reflecting recurring events such as holidays or weather patterns, and finally, the irregular component that accounts for the random or unpredictable variations in the data that cannot be attributed to the irregular or to the trend or the seasonal components. So what is seasonal adjustment? Well, it's basically the process of removing the seasonal component from the data in order to focus on more long-term movements. This is useful when seasonal patterns may mask other important dynamics. For example, let's say that we want to analyze the sales of a toy shop. If we look at the monthly data, it is likely that there will be a spike around Christmas. So comparing sales with other times of the year will not tell us whether the sales are really improving or it's just because of the festive season. So removing this pattern could help us to understand what is really happening with our data. This is a common practice in the economic field in order to better understand the underlying process driving the series and to allow more accurate forecasting and policy analysis. So next slide, please. Next slide, sorry. The pre-slide. Thanks. In 2009, the European Statistical System published their guidelines on seasonal adjustment with the aim of harmonizing European practices. The two most commonly used approaches are ARIMA model-based adjustment and fixed filter-based approach. Currently, at the Spanish Statistical Office, the methodology used is TRAMOSITS, an ARIMA model-based approach, which consists on two main stages. First, a REC-ARIMA model is fitted to the data to remove outliers and to account for calendar effects. And in the second stage, the signal is extracted using Wiener-Kolmogorov filtering. However, the series currently being processed at the Spanish Statistical Office cover many years, which means that the economic conditions, social dynamics, or other external factors may change, leading to shifts in the underlying patterns. For instance, the data suggests that the behavior of many economic time series changed following the 2008 financial crisis. These changes call into question the assumption that a single model can accurately capture the behavior of the entire series. So, faced with these challenges, there are two main objectives. On the one hand, to try to estimate the points at which the series change their behavior, which we call breakpoints. On the other hand, to propose a new general methodology for seasonal adjustment of long-term series. It is this latter objective which will be the focus of today's presentation. So, next slide. We consider a long-term series which includes A and B, the points where the series change its structure due to the effect of a certain event. So we can split the series in three different parts: the period before the event, the transition period, and the period after the event. We suppose that the pre and post-event series are stable and are considered to be modeled using ARIMA models, reflecting the different dynamics in these periods. So the question is, how can we model the transition period? Next slide.
Great, and you're almost out of time, so if you could just wrap up in the next 30 seconds, that'd be great.
Okay, sorry. It's just we propose to model it as a weighted average between the other two processes using a logistic function. And the logistic function includes a third-grade polynomial, so we need a change of variable that you can see in the slide.
All right, thank you so much. Great presentation. And then, so our last speaker for the speed session is going to be María Bugallo. So whenever you're ready, you can take it away and just let me know when you want me to go to the next slide.
Okay, hello and thanks for the introduction and good afternoon to everybody. So today I'm going to talk briefly about some methodological advances in the context of robust small area estimation. So to start with, we need to understand what is official statistics and why it's so important. By official statistics, here we cover any publication by a national statistical office based on a survey, on a census record, or on administrative data. And they are the daily life statistics because for many people, they represent, broadly speaking, the essence of statistics, including unemployment rates, poverty measures, and results related to the environment and also to health. And they should be used by policymakers in order to reduce inequalities. However, and although we live in an age of information, there is still a need for a cost-efficient survey design. On the one hand, we have the level of aggregation on the survey, and on the other one, the level of aggregation of the results. And it can be quite different, so we dealt with small area estimation challenges because the sample sizes are quite small to use direct estimators such as the Hayek or Joule-Thomson estimators, and we need to rely on more sophisticated prediction tools. So in the next slide, here we are gonna present the M-quantile modeling approach to small area estimation. Instead of using classical linear and generalized linear mixed models, the idea is to non-parametrically capture the variability of the population, apart from that explained by the auxiliary variables, using the best probabilities of a given area. This is a generalization of the quantile regression, a robust one, by using bounded influence functions. So here we are including also a toy example. The different areas are represented by different colors in the plot, and at union level, we feed different M-quantile regression surfaces in order to predict for the unobserved part of the population and therefore address the robust prediction of a given indicator, here based on an absolutely continuous random variable and also obtaining a trade-off between robustness and efficiency by fitting the tuning constant. And the novelty is to extend this M-quantile modeling approach to small area estimation to temporal data and develop a new time-weighted M-quantile methodology. By seeing the bigger picture and without focusing on the details in the next slide, I'm going to present the application to the Spanish living conditions survey, in order to predict income trends over time. This survey is designed by the Spanish National Institute of Statistics to obtain accurate direct estimates at autonomous community level, but here the aim is to do the research at a lower level of aggregation. Indeed, in 23 provinces of MP Spain. MP Spain covers those provinces that have lost inhabitants in the last decades or have a population density below the national average. And in order to improve the precision of the results, we include 10 years between 2013 to 2022 with the aim of predicting the equivalent disposable income that is a target variable very useful for obtaining poverty indicators. And as for the auxiliary information, we include 4 age groups and the sex of the respondent. So after fitting the model and addressing the plugin type prediction, we plot the results. Here in the maps, we can identify the changes over time and also the spatial variation. Indeed, the north traditionally richer, and on the other hand, the south and east, and in this case, the provinces of Extremadura and the north of Andalusia. So in the next slide, we finally also develop a methodology to estimate the coefficients of variation and to quantify the uncertainty of our results. And if we look at the legend, we can observe that the values are below 12.5% in all the provinces and also for all the time periods, and indeed below 5.5 for most of them. So, with this new M-quantile methodology with temporal dependencies, we are able to non-parametrically capture the variability, in this case between provinces, and also the temporal relationships, and improve the precision of classical linear and generalized linear mixed models, but also the precision of the robust approach, the M-quantile models. So if you are interested about our methodology, here I'm including the link for the GitHub project repository where our code is explained. And thank you very much for having this opportunity.
Great. Thank you so much, Maria. So that was our last speaker for the speed session, so we can get the next session started.